Hello everyone, this is going to be a video on solving Laplace's equation in 2 dimensions in a wedge-shaped region. And as I've illustrated in the diagram that I've sketched out here, our wedge-shaped region has an opening angle of theta naught. I've called the function that we're solving for v, and the boundary conditions are that v is held constant at a value of v naught along the two radial lines defining the edges of our wedge. Notice also I've put these dots just to illustrate that these lines extend forever, so that our wedge-shaped region is not bounded radially. It extends to infinitely large radii. Now, if you like, you can just think of this as a maths problem to be solved, or if you'd like some physical context, you can imagine that we've taken two semi-infinite conducting plates and joined them along a line. This line here, which looks like a dot because it's going straight into the screen, and we're holding those conducting plates at constant potential V0, and we're trying to solve for the potential in the region between them. This is actually a problem that I went through a little while ago on my channel using a different, slightly unconventional method using complex numbers. Just to be clear about the coordinate system that we're using, I have written V as a function of r and theta, where r and theta are just the standard 2D plane polar coordinates. I'm putting the origin of our coordinate system over there, and this already allows us to write down the defining equations of the two half lines of constant v. The horizontal one is just defined by theta equals 0, and the sloped one is defined by theta equals theta naught. So if we want v as a function of r and theta, then of course we also need to know what the Laplacian itself is as an operator in terms of r and theta. We could try and work in Cartesian coordinates, which would make the Laplacian simpler, but it would be very difficult to later apply the boundary conditions given the geometry of this problem. So here it is, the Laplacian in polar coordinates. I'm going to use this result without proving it. This is going to be our starting point. And the way that we're going to solve it is separation of variables. So we're going to look for solutions of the form v, which is a function of both r and theta, is a function purely of the radial coordinate, which I'm calling capital R, multiplied by a function purely of the angular coordinate, which I'm calling capital theta. So we're kind of specifying the functional form of the solution that we're looking for. So this is nice because it's going to end up turning our partial differential equation into two ordinary differential equations, one for r and one for theta, and we'll see in a few moments why that is. Let's just substitute this functional form into our differential equation, and the beginning stays the same, 1 over r d by dr. Now, you've also got your r in there, that doesn't change of course, but dv by dr, this is a partial derivative with respect to r, so when you differentiate v, which is all of this stuff, you only differentiate capital R. Therefore, you can write dv by dr as dr by dr. This can be written as a total derivative because big R only depends on little r. And then there's a theta which hasn't been differentiated, right, because we're just partially differentiating with respect to r. But we may as well put that outside the brackets because differentiating capital theta with respect to r doesn't do anything. Then we use the same logic for the second term in our PDE. You've still got your 1 over r squared, but now the second derivative of v with respect to theta only affects the theta part of our function. So the r just stays as it is, and you get, this is now total derivative d2 theta by d theta squared, and all of that's supposed to equal 0. Now you can tidy this up a little bit by writing it as two separate terms, one of which contains only the r terms, and the other of which contains only the theta terms, right? I'm also going to tidy things up by multiplying everything by r squared just to remove the fractions. So if we do that, your first term is going to be proportional to r. Then you've got this derivative term, which I'm going to abbreviate using dash notation for derivatives. So that's r, big R dash, and then all dashed because we're differentiating the whole thing. And in terms of how to actually separate out the r and theta bits, you can divide the entire thing by big R and big theta, because then what happens in the first term is the theta disappears and you get over capital R. And what's going to happen in the second term? Well, we got rid of this 1 over r squared. We divided by big R and big theta, so this disappears, and you end up with theta double dash over theta, and that's all equal to 0. Same equation, just tidied up a little bit. Now the key realization is that this bit here only depends on little r, and this bit here only depends on little theta, and yet we are supposed to add those two bits together and get 0. Now, the only way that can possibly happen, because r's are completely independent from theta's, is for each of those bracketed terms individually to be equal to a constant. In other words, it has to not depend on either of the coordinates themselves. So this first bit I'm going to call just k. This second bit has to be minus k because they have to add up to 0, right? And I'll just make a note that that k and that minus k, those are just constants. Now, so far, we don't know anything about what k can be, and so we need to basically consider all possible values of k, consider every possible case of values that k can take, so that we make sure we construct our fully general solution before we try to apply the boundary conditions. And we're going to consider the simplest case first. I'll call this case 1. We're going to consider what happens when k is 0. That will give us a particularly simple set of differential equations to solve. Now, the theta differential equation is easier because if theta double dash over theta is equal to minus k, which is just 0, then theta double dash itself is just 0, right? So we get the differential equation, theta double dash is 0, and then you just straightforwardly integrate that twice. You integrate once, and you get a constant, which we can just call alpha, and then you integrate again, and you get theta there, little theta, the coordinate, and then another constant of integration, which I'm going to call beta. So we've already solved for the case where k is 0 for our angular part. So what about the radial part? Well, all of that stuff is supposed to be 0. Again, that implies that just the numerator of that fraction is 0, and little r itself is not identically 0, and so we conclude that just that derivative term should be 0, right? So let's just write that down. Radial equation is r, big R dash, and then all dashed is equal to 0. We can integrate both sides because the left-hand side is just like the whole thing is being differentiated. So if we do that integration, the left-hand side is r, and then big R dash. I'm going to write that derivative out explicitly for reasons that you'll see in a moment. Now, let's just call the constant of integration gamma, next letter in the Greek alphabet. And this is a separable first order ordinary differential equation. All right, so keep the d big R on the left hand side, move the little r's to the other side, and integral of dr is gamma times the integral of dr over r, and that's a straightforward integral. You get gamma natural log of r plus another constant, which of course we are going to call delta. Note that I don't need modulus signs in my natural log because the radial coordinate r is positive by definition. So we've got theta, we've got r, then we can put together our overall solution because remember it's just big R times big theta, right? So function v is alpha theta plus beta, and then times gamma log r plus delta. All right, so we've solved our simple k equals 0 case. Now let's go on to consider the more general non-zero k case. And again, it's going to be easier to think about the theta differential equation first. So if theta double dash over theta is equal to minus k, that of course means that theta double dash is minus k theta. It's a pretty standard second order ordinary differential equation. Let's just be explicit about how to solve this. We do a trial solution, exponential trial solution. Let's say e to the lambda theta. This is simply because you're looking for a function whose second derivative is proportional to itself, and exponentials have that property. You differentiate this thing twice, and you pull down a factor of lambda squared. So the left-hand side of your differential equation becomes lambda squared theta. The right-hand side, of course, is still just minus k theta. Theta is not identically 0, so we can cancel down the theta from both sides. And you conclude that lambda is plus or minus the square root of minus k, or plus or minus I, times root k. So how should we interpret this, especially given that there's an I sitting in the front there? Well, there are two possibilities. One is that k is bigger than 0, then root k is real and lambda is imaginary. If lambda is imaginary, you have e to the power of a complex exponent, which is an oscillatory solution, right? Because of the relationship between complex exponentials and sines and cosines, right? So if k is positive, you get oscillatory solutions. If k is negative, then root k is imaginary. You times that by this I, and lambda turns out to be real, and then you get exponentially growing or exponentially decaying solutions. Now, of course, exponential functions and sines and cosines are really equivalent provided that you allow complex numbers in your solution. So it doesn't really matter ultimately what representation we choose. However, we can make life a bit easier by being informed by the boundary conditions and choosing the representation, in other words, exponentials versus trig functions, that seems the most sensible. And here, what I mean by that is that your v value is the same on the line theta is 0 and the line theta is theta 0. And so you don't really want your solution to be either growing or decaying as you go from the bottom plate to the top plate, right? You come back to the same value, and that suggests oscillatory solutions. So I'm going to choose to rewrite theta in terms of sines and cosines. I am going to say we're going to have to introduce some more letters here. Let's say the coefficient of the sine term is going to be a. So we've got a. Sine of, it's going to be root k theta, right? Because lambda was plus or minus I root k. Let's define another letter, let's call it p, to be root k. So sine of p theta, and then we're going to have b cosine term cos of p theta. We better make a note that p is the square root of k. There's a lot of letters at the moment, but we're going to eliminate most of them later on when we apply the boundary conditions. One other point I'd like to make is that it doesn't really matter whether we define p to be positive or negative. I'm going to explicitly state here that we're choosing p to be the positive square root of k. The reason it doesn't really matter is because, well, firstly, the cosine term, cosine is an even function, so if you switch the sign of p, that doesn't do anything. Sine is an odd function, so if you flip the sign of p, you basically get a minus sign in front of that whole first term, but that could be absorbed into a, right? And so physically they're not representing distinct solutions. Right, so that's the theta equation solved. What about this r equation down here? We are not saying it's equal to 0. This time we're saying it's equal to k. And so we're going to get a slightly harder looking equation to solve. You're going to have r times r, big R dash, all dashed, is equal to kr. And the first thing I'm going to do with this is just use the product rule to expand out that bracketed derivative term, or also just to minimize the number of letters we're using. I introduced this p for simplicity in the previous line, which was root k. So let's call k p squared and work in terms of p from now on. But if we use the product rule to expand those brackets, you've still got your prefactor of r. Differentiate little r, and you just get 1. So your first term is r dash. Then you need to leave the little r as it is, differentiate the big R dash, and you get r times big R double dash. Let's pull the p squared r to the other side as well. So we get minus p squared r equals 0, because it's always nice when things equal 0. And let's also just expand the brackets and reorder the terms into a more standard order and get r squared r double dash plus r dash minus p squared r is equal to 0. Now this equation looks a little bit difficult to solve at first because the coefficients of the derivatives are variable. They depend on little r itself. However, the equation has an interesting feature, which is that the order of the coefficient, in other words, r squared is second order, r is first order, and p squared is 0th order in r. The order of that coefficient always matches the order of the derivative, right? This is a second order derivative, first order derivative, and, well, 0th order derivative, in that you've done nothing. That suggests a trial solution of the form r being just a power law. So big R is r to some other power, running out of letters. Let's go to q this time. The reason that works is because each time you differentiate it, you reduce this power by 1, but the derivatives in the differential equation are all multiplied by an appropriate power of r to make sure that all of those terms will be proportional to r to the q. So in practice, how does that actually work out? Well, your first term, you're going to have r squared, differentiate this thing twice. Well, the first time you differentiate, you pull down a factor of q, then your power would be q minus 1, so you differentiate again, pull down q minus 1, and then you have r to the power of q minus 2 remaining. Similarly, for the second term, it's just going to be r to the q minus 1, and the final term is just p squared r to the q. And all of that is supposed to be equal to 0. Then notice that this r squared makes this minus 2 disappear, this r makes this minus 1 disappear, and then you've got an r to the q, common to all terms, right? So you get a simple polynomial equation for q, which is q squared minus q, then plus q minus p squared is 0. The linear terms cancel, and q ends up just being plus or minus p, which is a nice result. So then you can construct your solution, your full solution for the radial part. Some coefficient, which is, I'm going to call c because we used a and b for the coefficients of sine and cosine in the theta part, c times r to the power of p plus some other coefficient d times r to the power of minus p. So now we've considered all possible cases, both where k is 0 and where k is non-zero, and we're in a position where we can construct a general solution for v. Let's see if I have space to write this all out. The general solution will just be a superposition of all possible cases, right? So you basically add the solution for k is 0 to the solution for k being non-zero. So we're going to start with our k equals 0 solution, which was just alpha theta plus beta times gamma log r plus delta. Your non-zero k solution is going to depend on this parameter called p. We haven't said anything about what p can actually be yet, right? So for now, what I'm going to do is write down that we have to sum up all possible values. I'm just going to put sigma p, implying that we're summing over all possible values of p, right? We don't know what exactly that means yet because we haven't applied the boundary conditions, but it's going to turn out that there are certain values of p that are allowed. So all we have to do is multiply this with, where was it, the theta part, which is here. And so you're going to get c r to the p plus d r to the minus p. I should also actually index these coefficients by p because you might, in principle, have a different coefficient for each value of p. Right? So just to make that dependence explicit. And then we've got to multiply by the angular part. So a subscript p sine of p theta. And let's put the cos term down here. So plus b subscript p cos of p theta. So here's a nice general solution. Now we can apply our boundary conditions. Okay, so hopefully it's going to be quite satisfying to apply the boundary conditions and see how this huge general solution collapses into something a little bit simpler. The first thing we're going to do actually is notice that our wedge-shaped region contains the point r equals 0, in other words, the origin itself. That is going to cause problems with our general solution if we allow certain terms to be present. In particular, this ln r term is singular at r equals 0, as is this r to the minus p, which is 1 over r to the p. And so if we want our function v to remain finite, then we can't allow those terms to be present, right? So we can rule out those ones. Let me make a note of that. So v has to be finite when r is 0, which implies firstly that gamma should be 0. Also that all of the dp's should be 0, right, for every possible value of p. And there's one more thing we can do, following on from that actually, which is to note that if this term is not there, if that term is 0, then you're just left with a delta here. That delta is not really serving any purpose, right, because it's just multiplying alpha and beta, but alpha and beta themselves are currently free parameters. They can be anything. So we may as well absorb delta into the definitions of alpha and beta, which is equivalent to setting delta to 1. We can do that without any loss of generality. So say set delta equal to 1. And by a similar logic, we've gotten rid of this dp term here. This cp is serving the same function as delta. That is to say it's not serving any function at all. So we may as well set it to 1 as well for all possible values of p. So what do we have after we apply all of those simplifications? Well, you've got your alpha theta plus beta out the front. Your sum now looks a little bit simpler. Sum over some values of p. We set cp to 1, so you've just got r to the p, and then you've got your ap sine of p theta plus bp cos of p theta. Now we can go ahead and apply the boundary conditions where v is v naught along the lines theta is 0 and theta is theta 0. So firstly, let's just write down. We want to apply the fact that v at any radius when theta is 0 is v naught, and just use the previous line to see what happens. So if we substitute theta equals 0, this term will disappear. So you get beta, then the sine terms all disappear because sine of 0 is 0, and the cos terms all become just BP because cos of 0 is 1. And so we have beta plus the sum over some values of p of r to the p times BP. That stuff is supposed to equal V0. Now notice that beta is a constant. All of the terms in this sub are not constant. In particular, remember that I said earlier that p has to be positive. So r to the power of 0 is not included there. So every single term in that sum depends on r. So we can basically compare coefficients of each power of r, which is simple because there are no powers of r on the right hand side. So every single BP has to be 0 because those are the coefficients of terms which depend on r, but the right hand side doesn't depend on r. So we can say that BP has to be 0 for every p, and then simply beta has to be V0 to make the constant terms work out. So let's note down that beta is V0. So now let's apply our other boundary condition and see what the implications of that are. So V of r and theta naught is also supposed to be V0. So we go back to this expression here with our knowledge that the BPs are 0 and beta is V0. So maybe I'll just write that in there. So what do we get? We've got alpha theta naught plus V0 plus the sum over p of r to the p times a p sine of p theta naught. All of that is again supposed to equal V0. We can just get rid of this V0 and this V0 and put a 0 there. Now we can use the same comparing coefficients method that we used with the previous boundary condition. If we start off with the constant terms, well, the constant term on the left is just alpha theta naught. The constant term on the right is, of course, 0. That implies that alpha should be 0 because theta naught is non-zero. Otherwise, we wouldn't have a wedge at all. Now, we've got to be careful with this stuff, the r to the p terms. It would be tempting to think that all of the APs should be 0 by the same logic as before. However, that's not necessarily the case because the sine term could be 0, right? So AP could in fact be anything as long as your sine of p theta naught is 0 for each value of p. So we, well, equivalently, because sine of an integer multiple of pi is 0, that's like saying that p theta 0 is equal to n pi, where n is an integer, and let's say it's a positive integer because again we said that p itself was positive earlier on. And now we just go back and we've pretty much got our full solution. We just have to write it out. So v is equal to, well, this alpha term disappeared because we said alpha is 0. You've still got your V0. You've got your sum over values of p. However, we now know that p can only take on specific values defined by that relationship there, which links p to the positive integers. So instead of summing over values of p, it's easier to sum over the positive integers. So we can say n goes from 1 to infinity. There's no reason why you can't have arbitrary large values of n. And then you've got your coefficients. We called them AP before, but we're indexing the sum by n instead of p now. So let's call them an. Then you have r to the p, this thing here, but p is n pi over theta naught. So we've got r to the n pi over theta naught. Then you've got this sine of p theta, but again, you know what p is in terms of n here. So you get sine of n pi over theta naught times theta. And this is the specific solution to the Laplace's equation subject to these boundary conditions here. Interestingly, we've still got these undetermined coefficients here. So all that means is that the original problem didn't have enough boundary conditions to uniquely specify the solution. We could, for example, we could have like another arc-shaped surface here, and we specify some other potential there, and then we'd have another boundary condition to apply, and we could find out what all the various an coefficients are. But this is as specific as we can make it given these boundary conditions. You can also make some approximations if you like. For example, you can notice that if you only care about the solution close to the origin when r is small, then the smallest power of r is going to dominate. So you could, for example, only take the n equals 1 term if you wanted an approximation close to the origin. That's what I did if you've seen my other video where I solved this using complex numbers. You'll see the solutions are exactly the same. Okay, so that's all for now. Thank you for watching and see you next time.